Hello students, good evening. Welcome to today's Fluid Mechanics Crux Conclusion and Synopsis Classes. This is Sekhar from Msigma Gokulam. In the last class, I had explained about how to calculate the head loss due to friction for laminar flow and for turbulent flow separately. And we have got a different equations for Hagen-Poiseuille equation for the laminar flow and for the Darcy-Weisbach equation for the turbulent flow. But the Darcy-Weisbach equation can also be used for the laminar flow also in many cases. That is HF is equal to FLV square by 2GD, where F is called Darcy's friction factor, which is a dimensionless parameter. Head loss due to friction for fully developed flow through pipes can be calculated from Darcy-Weisbach equation given by FLV square by 2GD, where F is called friction factor, right? Now, so for laminar flow, when you equate the Hagen-Poiseuille equation and the Darcy-Weisbach equation, for the laminar flow, if you equate head loss due to friction from Hagen-Poiseuille equation and from the Darcy-Weisbach equation, you will get that friction factor is equal to 64 by Re, where Re is the Reynolds number, which is given by Vd rho by mu. So that means in laminar flow, friction factor is inversely proportional to the Reynolds number. But in turbulent flow, friction factor not only depends upon the Reynolds number but also depends upon the relative roughness of the pipe. In turbulent flow, friction factor not only depends upon Reynolds number but also on the relative roughness of the pipe. Obviously, rough pipes, pipes with more roughness will offer greater frictional resistance, therefore greater frictional factor, therefore greater head loss due to friction. Okay, rougher pipes will cause more head loss due to friction in turbulent flow, but whereas in laminar flow, whether a rough pipe or a smooth pipe does not matter, because friction factor depends only on the Reynolds number in laminar flow. Fine, that can be seen in the Moody's diagram also, you had shown you in the last class. So now having seen the equations for velocity distribution and the shear stress distribution in laminar and turbulent flows, now I will give the pipe networks. When the pipe networks are broadly divided into two categories: pipes connected in series, pipes connected in parallel. Okay. Pipe networks, even the pipes are connected end to end like this. When the pipes are connected end to end, this is a pipe 1, this is pipe 2, this is pipe 3, this is called as the pipes in series, end to end. Okay. And what is common? What is common for all the pipes will be the discharge. Q1 is equal to Q2 is equal to Q3. Here, when the pipes are connected in a series, Q1 is equal to Q2 is equal to Q3. Discharge is same throughout, but head loss due to friction, HF1 is not equal to the HF2 is not equal to the HF3. Okay, head loss due to friction will be the different, but the total head loss will be the HF1 plus HF2 plus HF3, whereas HF is given by head loss due to friction is given by FL V square by 2GD. Discharge is same, but the head loss due to frictions are different. The total head loss in entire pipe, total head loss in entire pipe will be pipes connected in a series, it is called end to end. Okay, and now here you can define an equivalent pipe. I could define a compound pipe. Equivalent pipe would have the same discharge as that of the Q1, Q2, Q3, same discharge, but also would have the say of the uniform diameter, same diameter, equivalent diameter, and the head loss of the equivalent pipe will be the same as the total head loss. So a compound pipe or the equivalent pipe which will be having the same diameter throughout having the same discharge as that of the pipes in connected in series, and also will offer the same total head loss here. Okay, so that kind of a pipe is called as the equivalent pipe. So this is one arrangement. Second arrangement will be pipes in parallel. Pipes in parallel. When the pipes are connected in series like this, discharge is same but the head loss due to frictions are different. And equivalent pipe is defined, or the compound pipe or the equivalent pipe is defined in such a way that if it is of the same uniform diameter, which would give the same discharge as that in the pipes connected in series, but also would give the same total head loss due to friction as that of the pipes connected in series. So you have the total head loss, this total head loss and head loss due to friction will be the same. We can assume the same friction factor for both the cases. We can calculate what will be the, unfortunately length is also same. The length of the equivalent pipe could be calculated from this equation. Discharge is same, total head loss is also same. The length of the equivalent pipe or the diameter of the equivalent pipe can be calculated from this equation. Now when the pipes are connected in parallel, pipes are connected in parallel like this. This is a parallel connection. When the pipes are connected in parallel, this is 1 and this is 2, Q1 will not be equal to the Q2, but the head loss due to friction, the total discharge will be the sum of the individual discharges. Q total will be the sum of the individual discharges, but the head loss due to friction in both the pipe will be the same. But HF1 is equal to HF2, that is F1 L1 V1 square by 2G D1 is equal to F2 L2 V2 square by 2G D2. This is when the pipes are connected in parallel, discharges will be different, but the total head loss due to friction will be the same between 1 and 2. Okay. Whereas when pipes are connected in series, discharge is same throughout, but the head loss due to friction will be the different. Here the head loss is same between 1 and 2, but the discharges will be different. Q1 may not be equal to the Q2, but the total discharge is Q1 plus Q2. This is called as the pipes connected in parallel. You have to remember these two kinds of the pipe networks. Now let me solve some of the problems regarding this incompressible flow through pipes. Fluid is flowing with an average velocity v through a pipe of diameter d over a length of L. Head loss due to friction is given by FLV square by 2GD, that is Darcy-Weisbach equation. In terms of the Reynolds number is 64 by Re. I already mentioned in the last class, this will be 64 by Re if the flow is laminar only. This equation 64 by Re, where Re is the Reynolds number Vd rho by mu, that is the ratio between inertia force and viscous forces. For fully developed laminar flow in the circular pipe, the head loss due to friction is directly proportional to the mean velocity. Not the square, it is the mean velocity in laminar flow. Fully developed laminar flow or viscous flow. For laminar flow through a long pipe, the pressure drop per unit length. So the pressure drop per unit length, head loss due to friction is given by delta P by W is 32 mu VL by W d square. It is called as Huygens-Poiseuille equation. So W gets cancelled. Delta P by L is directly proportional to the 1 by d square, that is inversely proportional to the inversely proportional to the square of the inversely proportional to the cross sectional area, just pi by, because cross sectional area is given by pi by 4 d square. So answer will be the C. Answer will be C from this. inversely proportional to the cross sectional area. You can see because A is equal to pi by 4 d square. Oil is being pumped through a straight pipe. The pipe length, diameter and volumetric flow rate all are doubled in the new arrangement because he has given the oil. When he mentioned the oil, definitely I would expect the flow to be viscous flow or laminar flow. Okay. Now I would like the frictional losses. Therefore, I would like to write the head loss due to friction for the laminar flow. 128 mu QL by pi W d to the power of 4. This is called as the Huygens-Poiseuille equation. 32 mu VL by W d square. So that could the velocity could be written as discharge by cross sectional area. You will get this. So in that case, what is in a straight pipe length, diameter, volumetric flow rate all are doubled. Q doubled, length doubled, this gets doubled. Okay, when this gets doubled, it will become 4 times more. But when this gets doubled, diameter 2 to the power of 4 means 16. 4 divided by 16, so 1 by 4. So that your ratio of the pipe frictional losses for the new arrangement will be 1/4 of the original, because Q gets doubled, L gets doubled, diameter also gets doubled. Pipe length, diameter and volume of Q gets doubled, length gets doubled, diameter gets doubled. When the 2 into 2, 4, when this gets doubled, 2 to the power of 4, 16, 4 by 16 will be 1 by 4. Answer will be A. Water is flowing through a horizontal pipe of constant diameter and the flow is laminar. Very clearly given, it is a viscous flow. If the diameter of the pipe is increased by 50%, keeping the volume flow rate constant, and pressure drop in the pipe due to friction will decrease by. So I need to write the HF in terms of discharge. 128 mu QL by pi W d to the power of 4. Now constant diameter is maintained constant, flow is laminar. If the diameter of the pipe is increased by 50% and keeping the volume flow rate constant, okay, 1.5 times it is increased, the the pressure drop is this, right? Delta P by W gets cancelled. Keeping this is maintained constant, same length. This is increased by 1.5 times. So it will get reduced, right? Because 1.5 times it is increased diameter. 50%, right? It has become 1.5 D. 1.5 to the power of 4, original one you have to compare. So you will get reduced, will decrease by 1.5 to the power of square to the power of square. So I think answer will be A answer. You have to just HF is delta P, or rather delta P is directly proportional to the 1 by D to the power of 4. So you can use this formula. I think answer will be A. For a fully developed flow of water in a pipe having a diameter, velocity V, the kinematic value of the Darcy's friction factor. Fully developed flow. First I calculate the Reynolds number, Vd rho by mu, or otherwise Vd divided by nu. Nu is the kinematic viscosity. What is the velocity there? 0.1, diameter is 0.1, kinematic viscosity is 10 power minus 5. So it becomes plus 5 divided by 100, it becomes 10 cube, 1000. It is 1000. The flow is laminar, because why the flow is laminar? Since Reynolds number is less than 2000. As long as the Reynolds number is less than 2000, flow can be taken as the laminar. Therefore, Darcy's friction factor is 64 by Re, that is 64 by 1000. This is answer. Coitus flow is characterized by, coitus flow is like this. There are two plates, parallel plates, parallel plates. Bottom plate is fixed and there is a liquid or a fluid, and we are exerting a force P, and we are moving with the top plate with constant velocity. So this kind of a flow is called as the velocity variation can be expected to be linear if the gap is very small, sometimes non-linear, we can say anything. This such kind of a flow is called as the coitus flow. Steady, incompressible between one fixed plate and the other moving plate with a constant velocity. Answer is D. By exerting a certain force, you are moving with constant velocity, right? Answer is D. Such flow is called as the coitus flow. Bottom plate fixed and the top plate is being pulled with a constant velocity V. Consider fully developed steady laminar flow of an incompressible fluid. What do you mean by incompressible fluid? Density is constant with viscosity mu. Through a circular pipe of radius r. Given that the velocity at a radial allocation of r by 2 from the center of the pipeline, the shear stress at the wall is K into U1 by R. First I will draw the figure. Circular pipe of radius r. Given that the velocity at a radial location of r by 2. How do the velocity varies? First of all, velocity varies parabolically. This is axisymmetric parabola. That is the velocity distribution. This is the velocity distribution. Given that the velocity at a radial location of r by 2 from the center line. So here at a distance of r by 2. Okay, from the center line of the pipe, this is the velocity is given by U1. The shear stress at the wall is K mu U1 by R. Okay, shear stress at the wall. Shear stress distribution will be like this. Shear stress at the wall will be tau max. Shear stress at the wall tau max is equal to minus dou P by dou X into R by 2. Okay. K into mu into U1 into R. Okay. Now this U1, if we just look at that, U is equal to minus 1 by 4 mu into dou P by dou X into R square minus R square. This is the velocity distribution. So this is U1 is equal to minus 1 by 4 mu into dou P by dou X into R square minus R by 2 whole square. So it becomes 2R square, this becomes 4, no? R square by 4. 4R square minus R square, it becomes minus 1 by 4 mu into dou P by dou X. This is the velocity distribution. 4R square minus R square, that is 3R square by 2. This is U1. U1 I will substitute that. So dou P by dou X, U1 I will substitute, implies minus dou P by dou X into r by 2 is equal to k into mu into what is that u1 minus 1 by 4 mu minus 1 by 4 mu into dou p by dou x into 3 r square by 2. 3 r square by 2. Now you could get the value of the q. Dou p by dou x will get cancelled. Minus dou p by dou x minus dou p by dou x will get cancelled. Mu will get cancelled. K mu into r, there is one more r is there. Q mu u1, this is u1. This is u1 into r will be there. There is one more r is here because this r is there. Now you can get the value of the k. Tau max is minus dou p by dou x into r by 2 given by q mu u1 divided by r. Sorry, I have put up the divided by r. Now this will be, this is divided by r. So this r will get cancelled. This r will come here. R square also will get cancelled. You will get the value of the q. Okay. This r will come to the left hand side, becomes r square. R square and r square will get cancelled. You will get the value of the k. So good question, previous gate question. He has combined the shear stress distribution and the velocity distribution. This is the velocity distribution. This is from the shear stress distribution. This r square will get cancelled because this r will come to the left side, r into r square, and this r square will get cancelled. You will get the value of the k. Fluid at the diverging pipe. Fluid at the diverging pipe of length L having inlet and outlet radii. This is R1, this is R2, and a constant flow rate Q. Assuming the velocity to be axial and uniform and at any cross section, acceleration at the exit. Okay. Q is equal to pi r1 square into velocity v1, which is equal to pi r2 square into velocity v2, right? The acceleration at the exit. Okay. A is equal to, actually it is a steady flow, constant flow rate, steady flow. dV by dt dou v by dou s into ds by dt. This is v into dou v by dou s. That is, this is acceleration. This is v into delta v by delta s. Acceleration at exit means velocity. Acceleration at exit will be velocity at exit into change of velocity. This is the delta v by delta s. V2 into what is that delta v change in velocity? V1 minus V2 divided by delta s is L. Now we can get the V2 there, Q by, now from this we can calculate what is the acceleration at exit. From these equations already got V2 is equal to Q by pi r2 square, V1 is Q by pi r1 square, a length is given there. We can calculate the acceleration at the exit. What is the delta V? Change in velocity from inlet to the exit. What is the change in displacement? L, for a length of L. Acceleration is dv by dt, dou v by dou s into ds by dt, v into dv by dou s, and for a length of L, dou v will be delta v and ds will be delta s. What is the delta s? Change in location, or change in length, or change in displacement, that is delta s. Delta v will be v1 minus v2. Here the velocity is v1, here the velocity is v2. Water at 25 degrees Celsius is flowing through a 1 kilometer long GI pipe of 200 mm diameter at a rate of 0.07 meter cube per second. Discharge is 0.07 meter cube per second. Darcy's friction factor is given 0.02. Length of the pipe is 1000 meters. Diameter is 0.2 meter. And the density of the water is 1000. Pumping power. Pumping power will be WQ into head loss due to friction. Pumping power required to maintain the flow, where W is rho G. Rho G into Q into HF. So many watts this is. This is in watts. Take care of, but answer is given in kilowatts. Rho is given, G is given, discharge is given. Let us calculate the HF from the Darcy-Weisbach equation, 2GD. The velocity we could obtain as FL by 2GD into velocity is discharge by pi by 4 d square whole square, because discharge has been given, diameter is given, velocity is equal to discharge by cross sectional area, right, from the continuity equation. Calculate HF, substitute here, you will get the pumping power in watts. This is the formula for the pumping power to maintain the flow. W is the specific weight, rho G, Q is the discharge, HF is the head loss due to friction. From the Darcy-Weisbach equation, mind that here you will get the answer in watts finally, but the answer is asked in kilowatts here. Please know the pumping power. You will get the answer in watts here. First get that head loss due to friction, substitute here. Discharge is given 0.07, friction factor given, everything is given there. Diameter is given 0.2 meters. From continuity equation, Q is equal to area into velocity. From that we calculated the average velocity or mean velocity. In the formula FLV square by 2GD, that velocity is the mean velocity of flow. Same is the case in case of the Huygens-Poiseuille equation also. In the Huygens-Poiseuille equation also, 32 mu V L by WD square, that V is the average velocity. In laminar flow, that average velocity of flow is exactly half of the maximum velocity. Water flows through a 10 mm diameter and 250 meter long smooth pipe at an average velocity was given, density given, viscosity was also given. Assuming fully developed flow, the pressure drop in the pipe will be. First let us calculate what is the Reynolds number, RE, to establish what kind of flow it is. We don't know actually in pipe flows how to establish whether a laminar flow or turbulent flow by calculating the Reynolds number, that is VD rho by mu. Yes, given mu also. Velocity is how much? 0.1. Diameter is 10 mm, that is 10 by 1000. Density will be 997. Mu has been given there, 855 into 10 power minus 6. You will get the Reynolds number. Once we get the Reynolds number, I think hopefully it is a laminar flow only. Hopefully it is a laminar flow. Okay. Maybe less than 2000. If it is less than 2000, the flow will be laminar. So the pressure drop is delta P by W is equal to HF is equal to 32 mu VL by W d square. That is a Hagen-Poiseuille equation. I guess the flow is laminar flow because the Reynolds number seems to be less than 2000 if we calculate that. And W gets cancelled. Pressure drop in Pascal. Delta P will be 32 into mu will be 855 into 10 power minus 6. Velocity has been given as 0.1. Length 250 meters divided by diameter will be 10 by 1000. All dimensions we have to keep it in meters. You will get the answer in Pascal. All dimensions, every linear dimension we have to substitute only in meters. No mm, no centimeter. 10 mm given diameter, therefore 10 by 1000 meters converted. So everything you have maintained the proper units. Final answer pressure drop will get in Pascal. This is the mu value 855 into 10 power minus 6. For a fluid of dynamic viscosity and density was given, flows with an average velocity of 1 meter through a long duct of rectangular section. For a rectangular section, we have to calculate the equivalent diameter. Okay. For a rectangular cross section, 25 characteristic dimension here will be, the characteristic dimension D will be 4A by P, 4A cross sectional area by P. Generally, such kind of ducts are used in the heat transfer also, in the convection heat transfer also. This kind of analysis is very useful for calculating the Reynolds number. For a non-circular pipes like this, non-circular ducts like this, the equivalent diameter or the characteristic dimension is calculated from 4 into cross-sectional area by perimeter, whereas this is the perimeter. So once we obtain that, then we can calculate the Reynolds number from VD rho by mu. First we have to calculate the, what is that CS? Cross-sectional area. Cross-sectional area 25 into 15 divided by P is the perimeter. ACS means cross-sectional area, remember, that is 25 into 15. And then calculate this diameter, we have to substitute here. Density was given, velocity was given, dynamic viscosity is been given, dynamic viscosity given, density given, velocity is given. You calculate the Reynolds number. Mostly if it is assuming a laminar flow, he has given the pressure drop. You can calculate delta P by W 32 mu VL by W d square. W gets cancelled. Everything is known. Mu is known. This is the mu. This is the mu value, right? This is mu. Everything is given. This is mu. Density is given. This is rho. This is rho. This is velocity. V velocity given. Every data given. You can substitute. The length also per meter length. You can take the LS. We can take the LS. Put L as 1 meter because he has asked the pressure drop per unit length. Velocity known, mu known, diameter known, everything is given. Diameter, but we have to keep it only in meters there. What is the diameter there? You have calculated diameter there. Here, equivalent diameter. Is a non-circular duct, no? For a non-circular duct, it is 4 into cross-sectional area by perimeter. This is the perimeter. 2 into 15 plus 25 mm, that is the perimeter. Consider fully developed flow in circular prop with negligible entrance effects, assuming the mass flow rate, density, friction factor, everything constant. If the length of the pipe gets doubled and diameter is halved, head loss due to friction. For fully developed flow with negligible density and friction factor also to be constant. So I will make use of the Darcy-Weisbach equation. Head loss due to friction is given by FL V square by 2GD, FL Q by pi by 4 D square whole square by 2GD. So mass flow rate is constant, m dot is constant, implies m dot is discharge into Q. Rho is anyhow a constant because it is an incompressible flow, implies Q is also a constant. Length of the pipe gets doubled. This gets doubled. Diameter is halved. This gets doubled. Diameter is halved. That is d into d square. Sorry, d power 5. That is HF is directly proportional to length and inversely proportional to the d power 5. Okay, diameter is halved, so length gets doubled, right? 2, this is 2 times gets doubled. Now the diameter is halved means 1 by 2. 1 by 2 to the power of 5, it becomes go to the up 2 to the power of 5 into 2 power 6, 2 to the power of 6 times. What is so HF increase by 2 to the power of 6 times. What is the 2 to the power of 6? 2 cube is 8. 8, you know, 8 again cube there. That is 64 times. Answer is this. 2 to the power of 4 is 16. 2 to the power of 5 is 32. Answer is D. 64. This gets reduced by, this gets diameter is halved. Okay, this length is gets increased by 2 times. So answer is 64. This is a previous gate question. 3 parallel pipes are connected and flow rate. 3 parallel pipes. Pipes are connected in parallel. Q1, Q2, Q3. Okay, the total discharge will be sum of the individual discharges and the head loss will be, the answer is B. When the pipes are connected in a parallel, when pipes are connected in parallel, head loss will be the same, but the total discharge will be the sum of the individual discharges. This question, in similar question was asked in gate 24 also in mechanical paper. Parallel pipe networks in parallel is asked. You may refer to that gate 24 paper also. Head loss will be the same. HF1 will be equal to the HF2 will be the HF3 which is equal to the total HF. But the total discharge will be the equal to the sum of the individual discharges. But when the pipes are connected in series, all the discharges will be the same, but the total head loss will be the sum of the individual head losses. The head loss for a laminar incompressible flow through a horizontal pipe is H1. Okay. Pipe length and fluid remaining the same, average flow velocity doubles and pipe diameter reduces to the, what is the HF formula? F, 32 laminar flow, 32 mu VL by WD square. Okay, average velocity gets doubled and the pipe diameter reduces to half. Okay, pipe diameter reduces to half. It gets doubled, it becomes half means 1 by 2 square is 4. 4 will go to the top, 4 into 2, 8 times. Okay, the ratio H2 by H1 will be 8. Answer is 8. So length remaining the same, fluid also remaining the same. Mu fluid remaining same means same viscosity, same length. Fluid, as long as the fluid remains same, mu remains same. This gets double, d becomes half. So 4 times 4 will go up, 4 into 2, 8, 8 times. Your head loss will increase by 8 times. Okay, this is halved, this is doubled, velocity gets doubled. Okay, simple Darcy, Hagen-Poiseuille equation, because the flow is given as laminar. Water at ambient temperature flows a horizontal uniform cross section at 1 kg per second. Mass flow rate given if the pressure drop across the pipe is 100 kilopascal, minimum power required to pump. Okay, head loss delta pressure drop across the pipe, delta P is 100 kilopascal. Pumping power WQ HF, HF will be delta P by W, W gets cancelled. What is that? Q will be mass flow rate divided by density, 1 divided by 1000, 1 divided by 1000, m dot is mass flow rate divided by densities. Okay, this is the discharge. Discharge is equal to mass flow rate divided by density into what is the pressure? 100 kilopascal, but I have to convert into the pascals there to get the answer in watt. Okay, head loss due to friction is delta P by W. Consider steady flow of an incompressible fluid is a gate question through two long and straight pipes of diameters arranged in series. It is a series. Both pipes are of equal length and flow is turbulent in both the pipes. Friction factor for the turbulent flow is given K into Re to the power of minus n, or positive constants K and N, Reynolds number, neglecting minor losses in the pipe 1 to the pipe 2. Okay. And turbulent flow, it is turbulent flow. Consider steady flow through a long straight pipes of diameter arranged in series. When they are arranged in series, discharge is same. Okay, ratio of the frictional pressure drop. Okay, delta HF will be equal to the delta P by W is F L V square by 2GD. Okay, that F is okay. Friction factor is written as K into Re to the power of minus n into length into discharge will be the same, right? Velocity will be the same. Now write velocity as Q divided by pi by 4 d square, Q divided by whole square to the power of whole square divided by 2G into D. Okay, because we know that discharge is equal to velocity into pi by 4 d square, area of flow. Discharge is equal to velocity into area of flow. Therefore, this velocity are written discharge divided by cross sectional area. The velocity I can written whole square there. Now, Q is same. Pipes in series. Pipes in series means implies Q is same in both the pipes. That is established. Okay. Reynolds number. Now I have to change the Reynolds number again. Reynolds number is equal to V d rho by mu, that is Q by pi by 4 d square, Q divided by pi by 4 d square into this d also I write as a small one, because Q by pi by 4 d square into d into rho by mu. Same fluid is flowing, therefore rho is same, mu is same. So it becomes Re is directly proportional to Q by d. So this Re I could replace it as the Q by d. So this is very important point here. K is a constant. K into Re I could write it as Q by d whole to the power of minus n into L into divide Q square divided by pi by 4 d to the power of 4 divided by 2g d. Now this is the final equation we got. Now this is the final equation. K is constant. Both the pipes are of equal length. Length is also same. Discharge is also same. So finally you are left with D there. Okay. Finally you are left with D. Therefore HF is directly proportional to what is the diameter, you have to check. K is same. D to the 1 by d to the power of minus n, 1 by d to the power of minus n. Here it becomes 4, here it becomes d, 4 plus 1 into d to the power of 5. So it becomes 5 minus n. So answer will be A. HF is directly proportional to the 1 by d to the power of 5 minus n. He has asked, the HF is nothing but delta P, W is same. So he has asked delta P1 by delta P2, that is D2 by D1. Answer is A. D2 by D1 whole to the power of 5 minus n. Because in this equation, Reynolds number also have changed. V d rho by mu. Velocity is Q by area, diameter is there, rho is there, mu is there. I have written mu and rho are same for both the pipes. When the pipes are connected, same fluid is flowing. Rho and mu are properties, they remain the same. So Reynolds number is directly proportional to the Q by D. I substituted here. Now finally I got this answer. Very good question. Only thing what you have to understand here is both the pipes are of the same length, because they are connected in series, Q is same. So I have written only the velocity in terms of the discharge and cross sectional area. Only the diameters are different. Too long, same length but the different diameters. So answer is A. Very good question. Previous gate question. Now you have done enough number of problems on the flow through pipes. Now I shall start a topic called as the bound theory of boundary layer. What is this boundary layer? Boundary layer concept. Boundary layer is a thin region. Boundary layer will be formed on any body. Whenever any viscous fluid, we should understand the boundary layer like this. Whenever any viscous fluid or a real fluid having some viscosity, maybe gas or a liquid, any real fluid which is having some viscosity, maybe more or lesser, when it flows over a solid body, or fluid is stationary and solid body is moving inside that, or body is stationary, a fluid is moving like this, a flat plate, something like a flow or a flat plate. A viscous fluid, a real fluid. Real fluid means having some viscosity. Ideal fluid means having zero viscosity. When a real fluid flows past a flat plate, because of the viscous influence, there is a thin region close to the solid boundary called as the boundary layer, inside which viscous effects are predominant. Only within this thin patch, because the thickness of this boundary layer is pretty small, that is why it is called as a thin region. So this is also called as the hydrodynamic boundary layer, also known as the velocity boundary layer. What is the prime reason behind the formation of this boundary layer? The fluid having viscosity and the fluid having velocity. A real fluid having certain velocity flows over a flat plate or any solid boundary. There is a thin region adjacent to the solid boundary, inside which viscous influence are predominant. As such, there will be velocity gradients. What is the influence of that viscosity of the fluid? There will be velocity gradients. So due to the viscous nature, this is called free stream velocity. This is called free stream velocity. This is the x coordinate. This is the y coordinate. And HBL means hydrodynamic boundary layer, also known as the velocity boundary layer. It is a thin region formed over a solid body inside which velocity gradients are present. At different locations, you see a different velocities. This u is 0 here. Because of the viscous influence of the fluid, there is one layer of the fluid got attached to the plate. This theory of boundary layer is very important for the mechanical engineers in the heat transfer subject also, convection chapter also. This is very important, boundary layer, because this is a chapter which we again study in the convection heat transfer problems. Of course, this boundary layer growth will be there for the internal flows also, but to some extent, not fully. Okay, once the flow gets fully developed for the flow through pipes, your boundary layer growth will become finished. Okay, but this is an external flow, not an internal flow, it is an external flow. There will be velocity gradients, dou u by dou y. The last layer, how long the boundary layer will be defined from the plate? The last layer would have a velocity which is equal to the 99% of the free stream velocity. Here the velocity, this layer is called as the stagnant fluid layer. Okay, so this is how we define a boundary layer. So I define hydrodynamic boundary layer is defined as a thin region formed over the flat plate, inside which velocity gradients are present in the normal direction to the plate. Why these velocity gradients are formed? Due to the viscous nature of the fluid. These are the velocity gradients. HBL is defined as a thin region formed over the plate inside which velocity gradients are present in the normal direction to plate. Please, you may chart in the chart box. You may chart in the chart box. Any doubts if you are having, you may interact with me here. These velocity gradients are formed due to viscous nature of the fluid. If the fluid is ideal, there would not have been any boundary layer at all. If the fluid is ideal or inviscid flow, then no boundary layer will form at all due to viscous nature of fluid. How do you define the HBl thickness? Hydrodynamic boundary layer thickness is defined as the distance from the plate up to the edge of the boundary layer where the velocity of the fluid approaches to the 99% of the free stream velocity. Outside this boundary layer, everywhere free stream velocities prevail. There are no velocity gradients. Everywhere outside the HBl, everywhere you see the free stream velocities only, no viscous influence. Whatever the viscous influence is there, you will see only within this thin patch. This delta, which is called as the HBl thickness, hydrodynamic boundary layer thickness, is a function of x. This distance is called, this location is called as the leading edge. This is called as the trailing edge. This is called as the trailing edge, that is the leading edge. So the delta increases. As x increases, the boundary layer grows. The boundary layer keeps growing there as such. Why it grows is because it takes some time for the momentum to get diffused. Momentum is diffusing in this direction. So it takes some time for the momentum to get diffused, and the rate of momentum diffusion in this direction is given by the kinematic viscosity, which is a property of the fluid. The kinematic viscosity of the fluid will tell about how rapidly the momentum can diffuse through the fluid layers in the normal direction to the plate. In the normal direction to the plate, how quickly the momentum diffusion can happen is indicated by the property of the fluid called kinematic viscosity. So that is why the kinematic viscosity many times is also known as momentum diffusivity. Momentum diffusivity is the other name of the kinematic viscosity, which is dynamic viscosity divided by density mu by rho. If the nu value is more, the delta value will be relatively more. I can say if the kinematic viscosity of the fluid is more, the value of the delta would be relatively more for a given free stream velocity. Different fluids have got different kinematic viscosity, right? Okay. Now, if we just this is how we define the hydrodynamic boundary layer. Then boundary layer thickness are defined. Boundary layer thickness is defined as the distance from the plate up to the edge of the boundary layer where the velocity approaches the 99% of the free stream velocity. Here one more definition it is given. This is called as the displacement thickness. It is delta star. Okay. Displacement thickness can be defined as, because of the flow of this real fluid, the streamlines, they gets displaced. The streamlines would gets dislocated or displaced in the normal direction. So displacement thickness is defined as the distance by which the streamlines in the fluid flow gets displaced because of the formation of the boundary layer. Okay, that the thickness is called as the displacement thickness. It has got two definitions. Displacement thickness is defined as the distance by which the solid boundary must be displaced so that the flow through that whatever the displacement thickness would exactly be equal to the flow retarded because of the boundary layer formation. The displacement thickness is defined as the distance through which the solid boundary must be moved in the normal direction so that the flow of the fluid through that displaced distance, the flow rate of the fluid through the displaced distance would exactly be equal to the retarded flow because of the boundary layer formation. Or otherwise simply it can be understood as displacement thickness should be understood as the distance through which the streamlines must be displaced because of the boundary layer formation. These streamlines are moving. Because of the boundary layer formation, the streamlines gets displaced in this direction like this. By what distance the streamlines gets displaced in the y direction because of the boundary layer formation, that is called as the displacement thickness. It can be written like this. Okay, now the boundary conditions of the boundary layer I am explaining. The boundary conditions of HBL. At any given x, if delta is the thickness of the HBL, at any given x measured from leading edge, at y is equal to 0, u is equal to 0, at y is equal to delta, u is equal to 0.99 into v infinity, at y is equal to delta, dou u by dou y is equal to 0, at y is equal to 0, dou square u by dou y square is equal to 0. These are the four boundary conditions of the hydrodynamic boundary layer. At y is equal to delta, the dou u by dou y becomes 0. This dou u by dou y, the tangent, it keeps decreasing in the y direction. As you go from here to here, this dou u by dou y keeps decreasing and finally it becomes 0 here. This dou u by dou y is maximum at y is equal to 0. At y is equal to 0 here, because y has got two limits, 0 and delta. At y is equal to 0, dou u by dou y is maximum. That is why dou square u by dou y square is 0. When you call this boundary layer as laminar, actually, again the question comes, is the hydrodynamic boundary layer is termed as laminar or turbulent? For that, again we have to calculate the Reynolds number, local Reynolds number. Let local Reynolds number Rex is equal to V into infinity x rho by mu, where x is the distance measured from the leading edge. All the x values are measured from the leading edge. That is called as the local Reynolds number, because that Rex will be changing with x. You have a different Rex here, you have a different Rex, you have at different locations different Rex. Okay, or V infinity into x by nu. So if Rex is lesser than 5 into 10 power 5, implies flow is laminar for flat plates. Please note that one. This condition applies only for the flat plates. If it is greater than the 7 lakhs, the flow will be turbulent. Mostly the flows will be laminar only. Mostly the flows would be laminar flows only. If REX, if the local Reynolds number is greater than 7 into 10 power 5 for smooth plates, the flow is turbulent flow. For the smooth plates, for the smooth flat plates, all these criteria for the flat plates, for flow over a flat plate. So they are the criteria to call whether the boundary layer is laminar or turbulent. REX is called as the local Reynolds number. Why it is called local Reynolds number? Because as the X value changes, that REX also keeps changing. Okay. So what are the predominant forces acting over the element within the boundary layer? What are the predominant forces if you take the element? One is viscous force and inertia force. These are the predominant force that will be acting over the fluid element. Viscous forces and inertia forces. Pressure forces can be neglected. The equations of boundary layer I write. The equations of motion for boundary layer. Dou u by dou x, this is the continuity equation for two-dimensional flow. Dou v by dou y is equal to 0. This is a continuity equation which is valid for a steady incompressible flow. For steady incompressible flow, this is a continuity equation is valid. First one. Second one will be Navier-Stokes equation. X minus 1 by rho into dou p by dou x plus mu by rho into dou square u by dou y square is equal to Ax. This is the of course body force can be neglected. This body force potential that gravity force potential can be neglected for the x direction. So this is called as the Navier-Stokes equation of motion. Because we are having the fluid has got the viscosity. It is a second order equation. See that mu by rho is nu, no? Navier-Stokes equation of motion. And third will be 1 by rho into dou p by dou y is equal to 0. So these are the three equations of motion for the boundary layer. It is a second order equation. You may notice that it is a second order equation. This is a convective acceleration. Because in the boundary layer is formed for a real fluid. That is why the viscosity is coming into picture. Earlier I had given the Euler's equation of motion in the earlier cases. Euler's equation of motion is written for a steady, incompressible, irrotational or inviscid flow. Euler's equation of motion. Whereas this Navier-Stokes equation of motion is written for a real fluid, because boundary layer is formed because of the real fluid flow, fluid having viscosity. Okay. So this is a second order equation. So these are the equations of motion. Usually for flow over flat plates, dp by dx, no pressure gradients are taken as 0. Usually for a flow or flat plates, dou p by dou x is equal to 0. This will become 0. Only you will have this one for the flow or flat plates. dp by dx is taken up, no pressure gradients along the x direction. Right? Now, by integrating that momentum equation, Navier-Stokes equation of motion, with the help of the boundary conditions, we get the usually the velocity distribution. For flow or flat plate. At any given x. Measured from leading edge, this is the velocity distribution, where delta is equal to HBL thickness at that x, which is given by 5x by root of REX. This is also called, famously known as, Blachier solution. This is famously known as Blachier solution. That means delta is directly proportional to the x to the power of half. We may notice that. This delta is directly proportional to the x to the power of half. And this local wall shear stress, because of the viscous influence, there is a viscous drag, right? There is a local wall shear stress. Wall shear stress, dou u by dou y at y is equal to 0, no? At this location, the wall shear stress will be there, no? This is given by mu into dou u by dou y at y is equal to 0. This is called local wall shear stress. Many times this local wall shear stress is also given like this: CFX, local skin friction coefficient, into velocity head. Generally this is called as the skin friction coefficient or local drag coefficient. It is also called as local drag coefficient. All these formulae we have to remember. Why this local wall shear stress? Because of the velocity gradients, because shear stress is directly proportional to the velocity gradient. Why is called as a local wall shear stress? Because we are calculating the shear stress on the surface of the plate. It is called as the wall shear stress. Why it is called as a local wall shear stress is because it is changes with, we can easily say mu into 3 by 2 into, you can see in the previous equation, if you differentiate this, mu into V infinity into 3 by 2 delta. Mu into V infinity into 3 by 2 delta. Since this delta is directly proportional to the x to the power of half, these two being constant, local wall shear stress is directly proportional to the 1 by root x. Remember this local wall shear stress indicates the drag force, exerted by the fluid on the plate. What is the significance of this local wall shear stress? It indicates the drag force. Exerted by the flowing fluid on the flat plate. When the fluid is flowing on the flat plate, how much frictional drag, how much viscous drag exerted by the fluid on the plate is given by this formula. Okay. Look at this. The predominant forces acting on an element of fluid in the boundary layer or a flat plate in a uniform parallel stream are. What are the predominant forces acting on the fluid element considered inside the hydrodynamic boundary layer? Viscous forces and inertia forces. Answer is B. Viscous and inertia. Okay. The viscous forces and the inertia forces. Answer is B. And we always neglect the body forces and pressure forces also we don't consider. Viscous and inertia forces we consider. While using the boundary layer equations, Bernoulli's equation. So, can you write the Bernoulli's equation within the boundary layer? No, because Bernoulli's equation assumption is that the fluid is assumed as inviscid or the flow is assumed as irrotational. So, can be used only outside the boundary layer. We can write the here only. We can know because here the fluid is termed as inviscid flow. Here the fluid is termed as inviscid flow. Therefore, we can write the Bernoulli's equation only outside the boundary layer, because inside the boundary layer where the fluid viscous influence is predominantly present. What is basically a boundary layer? Inside which we see clearly the viscous influence. Answer is B. So look at this. This is one good question there. Is a common data question. A smooth flat plate with a sharp leading edge is placed along a gas stream. The U is coming with 10 meters per second. The thickness of the boundary layer at RS is 10 mm. Here it is 10 mm. The breadth of the plate is 1 meter into the paper. In this direction it is 1 meter. Density of the gas was given. Assume that the boundary layer is thin, two-dimensional and follows a linear velocity distribution. Here it is a linear velocity distribution. Earlier velocity distribution I had given was a cubic, but here the velocity distribution is taken as a linear at the section RS, where y is the height from the plate. This is a y direction. This is the y direction, right? Now what is being asked is the mass flow rate across the QR. He is asking what is the mass flow, this one. What is the mass flow rate here? See, if you take this as the control volume, this is the control volume, no? There is a mass entering here. There is a mass leaving here. There is a mass leaving here. You know, this is a mass leaving. This is the control volume. This is leaving. This is leaving. But this here it is entering. Therefore, for the steady flow, the sum of the masses entering should be equal to the sum of the masses leaving. If you want to get this, first get this and get this, take the difference, because this is leaving, this is leaving, this is entering. So first I calculate what is the m dot through PQ. That is rho. What is the area there? Rho delta, no, this distance, this height, rho delta, rho area, what is the area there? Delta into 1, so velocity will be u, so many kg per second through PQ. Then m dot through RS, this one. So if for that I take a small differential height, d by. So for that, what is that area mass flow rate through that differential height d by? Rho here we know, rho, what is the area there? dy into 1 into velocity u. This is u, no, small u, that is, this is a small u. Rho e to, and between the limits 0 to delta. Now I substitute rho, what is the u distribution? U is given u into y by delta into dy between the limits 0 to delta. You can easily calculate this. Rho u you can take it outside, and delta also we can take it outside. Integral y square, integral y means y square by 2, put that limit, that is rho u by delta into, that is y square by 2. After substituting the limits, it is delta square by 2. So this is the m dot through RS. Therefore, mass flow rate through QR is equal to mass flow rate through PQ minus mass flow rate through RS. Mass flow rate through PQ we know, mass flow rate through RS we know. Delta we can take this. Delta value is given. What is the delta? Rho is given. Delta value is also given. Yeah, 10 mm there. See, the boundary layer thickness, delta is given as 10 mm. Substitute that every value. Rho is given, u is given. This u is given as 10 meters per second, capital U. This is the small u. That is, this is the small u. Capital U is the free stream velocity. So whatever the mass flow rate here is this mass flow rate entering minus this mass flow rate leaving. Okay, this is how we can. So because this is a control volume, there is mass entering here, there is mass leaving here, there is a mass leaving here. Sum of these two masses should be equal to the mass entering for the steady state conditions. That is a conservation of mass. Okay. The integrated drag force between the PS will be. So again, we have to write the conservation of momentum. What is the drag force he is asking? To get the drag force, now again the same logic. What is the momentum entering here? What is the momentum leaving here? Okay. What is the momentum entering? What is the momentum leaving? So the rate of momentum leaving minus the rate of momentum entering will be the there is a momentum entering, there is a momentum leaving, there is a momentum leaving. So the drag force on plate is equal to the rate of momentum leaving minus the rate of momentum entering. What is, how to write the rate of momentum? Momentum, we know that I already explained yesterday also. This is the impulse momentum equation. Momentum is equal to mass into velocity. Mass into velocity, right? Rate of momentum means mass flow rate into velocity. It has got the units of Newton. What is the rate of momentum entering there? Look at this. What is the rate of momentum entering? here. This is the entering there, So m dot into m dot, the mass flow rate we have already calculated, mass flow rate through PQ, this one, into U. See, rate of momentum entering will be here, rate of momentum entering, rate of momentum entering through PQ. Entering through PQ will be mass flow rate through PQ into velocity U. That we know clearly. Mass flow rate through PQ we already calculated. Then, what is the rate of momentum leaving through RS? That should be calculated properly. Rate of momentum leaving through RS. So, for that you have to take a differential height, a small differential height d by. Look at this. Then what is the rate of momentum leaving through this d by? M dot into U. What is that m dot there? This is m dot. See this, rho A into U. That means rho into dy into 1 into U square. Rate of momentum leaving through RS. Integral rho, area will be dy into 1 into U square. Because this is up to here mass flow rate into velocity between the limits 0 to delta. You will get that rate of momentum leaving through RS. And there is one more rate of momentum leaving through QR here. What is the rate of momentum leaving through QR? What is the mass flow rate leaving through QR? We have already calculated. That into the free stream velocity. Okay. Rate of momentum mass flow rate through QR into free stream velocity U. Okay. So, if you substitute all the things, you will get the drag force. You know the mass flow rate leaving through QR, that into the velocity, the free stream velocity, that is the rate of momentum leaving. So, according to the impulse momentum equation, the drag force will be the rate of momentum leaving minus the rate of momentum entering. Look at this here, delta star, the displacement thickness. Between the limits 0 to delta. That is integral 0 to delta 1 minus sine pi y by 2 delta dy between the limits 0 to delta. So, get the delta star, divide with the delta, you will get the local displacement thickness. Delta star is the local displacement thickness. That this u by v infinity you can substitute here, then you will get the delta star by delta. Sin pi y by 2 delta is cos pi y by 2 delta divided by pi by 2 delta divided by pi by 2 delta, and substitute that and put the limits, and you will get delta star. Divide that with the delta to get the ratio. Look at this. The aerodynamic drag on a sports car depends on its shape. The car has a drag coefficient of 0.1 with the windows and the roof closed. When with the windows and the roof open, drag coefficient becomes 0.8. Car travels at 44 km per hour with the windows and the roof closed for the same amount of power needed to overcome the aerodynamic drag with the windows roof open is. Same power. Car is traveling with windows and roof closed. When the windows and roof open, the drag coefficient is becoming 0.8. Before when the windows and roof closed, the drag coefficient is 0.1. So, for the same power, power is equal to viscous drag into force into velocity, right? What is the viscous drag? Stress into area into velocity. Stress could be taken as coefficient of drag into rho V infinity square by 2 into area into velocity. That means power is directly proportional to coefficient of drag into, because same fluid, same area, that means V infinity cube. Okay. So, now this product, right? So, CD1 into V infinity 1 cube is equal to CD2 into V infinity 2 cube for same power. What is the CD1? Initially coefficient of drag 0.1, and when the car travels at 44 cube is equal to CD2 has become, CD2 is 0.8 when the windows open, roof open. What is the, you will get the, because see, density of air and frontal area may remain constant. Area same, density also same. Okay. So, we will get the, what is the speed of the car when windows are open. Drag is equal to stress into area into velocity. This shear stress is always given by coefficient of drag into rho V infinity square by 2. Area remaining same, see that. Area remaining same, he has mentioned density remaining same, area also assumed to be the same. For the same power, you will get the speed of the car when the windows are open. Air is with a velocity of 2 flows over the top surface of a flat plate. If the average value of the friction coefficient is the total drag force per unit width. Friction coefficient is average value, Rex. First, this CF bar average value will be 1.328 by square root of REL. L is the length of the plate, right? 1.328 square root of V infinity into rho by L. Sorry. V infinity into L by nu kinematic viscosity. He has given me calculate that, and drag force will be the average drag coefficient into rho V infinity square by 2 into area. Area will be per unit width. Area we can take it as the length into 1. Density is given, V infinity is given. What is that V infinity here? 2 meters per second. This is an average drag coefficient. Generally, local skin friction coefficient will be 0.664 by square root of REX. This is the local coefficient, local drag coefficient. The average drag coefficient will be double to the skin friction coefficient at the double the local skin friction coefficient at the trailing edge. This is the average. CF bar means average drag coefficient. He has mentioned clearly. Average value of friction coefficient or drag coefficient. You have to remember this formula thoroughly. In the boundary layer theory, in the theory of boundary layer, the most important concepts to be remembered are how to calculate the drag force, how to calculate the local shear stress, how to calculate the local boundary layer thickness delta, how to calculate the local displacement thickness delta star. These are the main things. In the theory of boundary layer, the main things that will be asked in the gate examination are: what is the meaning of local skin friction coefficient or drag coefficient, local wall shear stress, local boundary layer thickness, local displacement thickness. Okay, these are the main parameters. Here the questions are widely asked. Okay. Just take 5 minutes break. After the break, I will continue. Hello students, welcome back to the class after the break. In fact, here the area of the plate is taken as length into width, but the per unit width is mentioned. Per unit width of the plate, actually, that is why we have calculated the drag force in Newton. Remember, drag force formula is stress into area. Stress is given by average drag coefficient into rho v infinity square by 2. This is a formula for the average drag coefficient, which is a dimensionless parameter, where REL is the, what is this REL? Local Reynolds number at the trailing edge, at x is equal to L, or trailing edge. That trailing edge means the edge of the plate is called as the trailing edge. Plate has got two ends. One is called leading edge and this is called as the trailing edge. Consider laminar flow over a flat plate of length 1 meter. Laminar flow. Plate length is 1 meter. Okay. If the boundary layer thickness at a distance of 0.25 meter from the leading edge, this is called as the leading edge. I already mentioned this is the leading edge. This is the trailing edge. This at x is equal to L, which is equal to 1 meter. That is the trailing edge. At 0.25 meters, the boundary layer thickness at 0.25 meters from the, that is from the boundary layer thickness, delta is 8 mm. Then the boundary layer thickness at a distance of 0.75. At a distance of 0.75 meters, what is the boundary layer thickness? I already mentioned delta is directly proportional to the x to the power of half. Implies delta 2 by delta 1 is equal to x2 by x1 whole to the power of half. Implies delta 2 is equal to delta 1 is how much? 8 mm. 8 mm into what is x2? 0.75 meters. x1 will be 0.25 to the power of half, that is 8 into root 3 mm. This is the answer. Delta varies, see delta is increasing, this is the boundary layer thickness. Delta increases with x, as x increases delta increases. Okay. Delta is directly proportional to the root x in laminar flow. This is only for the laminar flow. An incompressible fluid flows over a flat plate with zero pressure gradient. I always suggest that whenever there is a flow over a flat plate, dP by dx is taken as zero pressure gradient, dP by dx, and anyhow dP by dy, anyhow it is a 0 within a boundary layer. The boundary layer thickness is 1 mm at a location where the Reynolds number is 1000. Reynolds number is 1000 means flow is laminar. Boundary layer thickness is 1 mm at a location where the Reynolds number is 1000. If the velocity of the fluid alone is increased by a factor of 4, then the boundary layer thickness at the same location will be. Okay, at some location delta will be 1 mm, right? And the Reynolds number is, where the Reynolds number is 1000. That means flow is laminar only. If the velocity of the fluid is alone is increased by a factor of 4, delta will be equal to the 5x by root of Rex. This is called Blassius solution. 5x divided by root of V infinity into x by nu. Okay. At the same location, same fluid. If the velocity of the fluid alone is increased, then the boundary layer thickness at the same location is asking, and the same fluid, that is same kinematic viscosity, that is delta is directly proportional to 1 by root of V infinity. Now when it is increased by 4 times, delta will decrease by 2 times. Delta, when the decrease is 2 times, means that will become 0.5 mm. It will become half. delta 2 will be, delta 1 is 1 mm, delta 2 will be 0.5 mm. Why 0.5 mm? Because root of 4 will be 2. So it reduced half. Delta will be getting reduced by half because this free stream velocity has been increased by 4 times. Same location, at this he has not changed the location, same fluid is coming. Because the same fluid is coming, the kinematic viscosity value also will be the same because kinematic viscosity is a property of the fluid. Same fluid is coming, same kinematic viscosity. Answer will be C. It is also previous gate question. Look at this, for airflow over a flat plate, velocity u, this is the free stream velocity u infinity, is given u into 3 by 2 into y by delta minus half into y by delta whole cube. Actually, it should be 5x by root of Rex, but this is an approximate solution, 4.64x we may take. If the free stream velocity is 2 meters per second, and air has a kinematic viscosity and density has been given, the wall shear stress at x is equal to 1 meter. Wall shear stress at x is equal to 1 meter. You have to write the Newton's law of viscosity. Wall shear stress mu into dou u by dou y at y is equal to 0. What is mu? Mu into density into dou by dou y of u. What is that u? U infinity into 3 by 2 y by delta minus half into y by delta whole cube at y is equal to 0 after differentiation. It will become nu into rho into u infinity, you can take it common. Okay, you can take it outside. It become 3 by 2 delta, after differentiation it will become 0. You have to just substitute there. Delta value has been given. What is the boundary layer thickness? Boundary layer thickness is not there, you have to calculate that. Delta will be 4.64 into 1 by root of v infinity into x by nu. First you have to get this delta at x is equal to 1 meter. After getting this delta, because I know the u infinity, this is u infinity, right? I know the u infinity, I know the x value, I know the kinematic viscosity, but first get this delta in meters and substitute that delta here, because density is known, u infinity is given, everything is known, kV is there, kinematic viscosity, we can see all the values here. Kinematic viscosity is there, density it is there, this is rho, and velocity is there, no? Velocity, this is u infinity is 2 meters per second has been given, everything is there. Kinematic viscosity is there. You can first get this delta, and after getting delta I substitute here, because because dou u by dou y at y is equal to 0, because it is this velocity gradient is required to get the wall shear stress. To get the wall shear stress, that means what do you mean by wall shear stress? The shear stress that has been calculated on the surface of the plate, that is called as the wall shear stress, which is calculated from the Newton's law of viscosity. This is the Newton's law of viscosity. Wall shear stress means shear stress calculated on the surface of the plate. Then why I have kept the dou u by dou y at y is equal to 0? Because this is a y coordinate, this is the x coordinate. On the surface of the plate means this y value is 0, because this velocity gradient is different at different heights of y. This velocity gradient is different at different values of y. But why I require at y is equal to 0? Because we want to calculate the wall shear stress. Wall shear stress means the shear stress on the surface of the plate. What is the significance of the wall shear stress? It otherwise indicates how much drag force, how much frictional drag, how much viscous drag the fluid will exert on the plate. That is indicated by the wall shear stress. Wall shear stress directly indicates the drag force. Consider a laminar flow at zero incidence over a flat plate. The questions of the boundary layer regarding the flat plate are very common in the GATE. Okay, the shear stress at the wall is denoted by tau wall. The axial positions xn on the plate are measured from the leading edge. Here at x is equal to 0, here at x1, here at x2. Up to here it is x1, up to here it is x2. This is x2. And he is asking x2 is greater than x1. So I already mentioned, tell that local wall shear stress is directly proportional to the 1 by root x. Therefore, a local wall shear stress at x2 is x1 is lesser than the x2. Answer is D. Local wall shear stress varies inversely proportional to the root of the x. All the x values are measured from the leading edge where x value is 0. Answer is D. Sorry, x1 will be more. X1 will be more because x is increasing. X1 will be more. Answer will be C. Local wall shear stress at x1 is greater than the local wall shear stress at x2. As x increases, local wall shear stress decreases. It is also a frictional resisting force. I think I already done this problem. Flow is assumed to plane coated flow. This problem I already done it earlier. Frictional resisting force. Resisting force will be equal to the stress into area. Stress is equal to mu into dou u by dou y into area. Area will be pi dl. That is mu into tangential speed by the gap into pi dl. The gap is given, this is the gap. The shaft is rotating inside a bearing. This gap is the oil, right? This is all oil. This is the shaft is rotating. This is the gap. Tangential speed is also given. Tangential speed given, y gap is given, d is given, length of the shaft has been given. Dynamic viscosity is also given. We can easily calculate the resisting force. This problem earlier also done it. Now this is the similar problem which I have done earlier. The rate of the mass flow leaving through the horizontal section beat. Here there is a mass entering. M dot BA mass entering here. That is M dot DC, mass is leaving. Here this is M dot BD. This mass is leaving, this mass is leaving, this mass is entering. Therefore, for steady flow, the rate of mass entering should be equal to the rate of mass leaving. For steady, because conditions are steady. For steady flow, what is mass entering? M dot BA should be equal to the M dot BD plus M dot DC. What is M dot BA? We can easily calculate rho. Area will be this height delta. Per unit width you can take per unit width you can take, that is perpendicular to the plane of the figure. Area will be delta into 1, velocity will be u naught, that is over. What is M dot CD? That is should be integrated. Integral, if you just take the dy, dy distance, rho, what is the area there? Dy into 1 velocity. What is the velocity there? Velocity distribution has been given here. Here the velocity distribution has been given. If this is dy, at that location velocity has been given here. U naught into 2 into y by delta minus y by delta whole square. Now you have to integrate this. Take the dy right side and you can integrate. Everything is known, m dot into cd. Therefore, mass flow rate through BD, this one will be m dot into BA minus m dot through DC, which we get it here. You can write this dy into 1 last. Rho is constant, take it out, u naught constant, and you can differentiate this. 2 by delta it becomes, it is y cube by 3, and put the limits between 0 to delta. Okay. Now you will get m dot into cd. Now you will get this mass will be this mass entering minus this mass leaving will be the m dot into bd. This question was, similar question was I have done earlier also. This is a simple question that is consider fully developed steady state incompressible laminar flow between two large parallel horizontal plates. Top plate piece is a coet flow. Flow is coet flow. Coet flow means bottom plate is fixed. Bottom plate is fixed and the top plate is moving with a constant velocity. That is 4 meters per second. Separation is 5 mm. Gap between the plates is 5 mm and no pressure gradient, and the velocity varies. Top plate moves with a constant velocity, and velocity variation we can take it as the linear. Nothing is mentioned. We can take the velocity variation as linear. Okay. So he has asked the average shear stress. Tau is equal to mu into dou u by dou y. Mu into v by y. We can take kinematic viscosity. Mu is equal to kinematic viscosity into density. Nu into rho into v by y. Everything we know. Kinematic viscosity we know. Density we know. Velocity we know. Velocity is u. Velocity we can take it as a u there. U by y as given. U is 4 meters per second. Y is gap 5 mm. All are there. Then you can calculate the viscous stress. Okay. Now I will do another important topic in fluid mechanics called as the dimensional analysis. Very important thing there. This technique is a mathematical technique which is used in the heat transfer also, fluid mechanics, hydraulic machinery, heat transfer, many subjects it is used. What is the main use of this is, whenever any functional relationship is there, which is containing a large number of variables, all these variables can be grouped into a lesser number of dimensionless pi terms. Okay. Dimensional analysis is a mathematical tool which helps us in reducing the large number of variables in any functional relationship. If there are so many large number of variables are there, all these variables can be grouped into a lesser number of dimensionless pi terms, dimensionless pi groups, and the functional relationship can be expressed in terms of those dimensionless pi terms. So that is a very useful mathematical technique. Okay, in fact, this has got two different theorems. One is called as the Rayleigh theorem and other thing is called as the Buckingham pi theorem. Buckingham. Generally, Rayleigh theorem is used only for when the number of variables are lesser, maybe 3 or 4 like that. Whereas the Buckingham pi theorem is much more useful even when the number of variables may be 7, 8 or so, that theorem can help us. Usually that is more prominent, more famous. This is useful only when the number of variables are lesser, like this. In a functional relationship, if there is a variables are like this, and we can find these exponents by equating the dimensions. So x is a dependent variable, x1 is a independent variable. These are all the independent variables. We can write the exponents like this by equating the dimensions on both sides. The dimensionals on both sides, we can get exponents a, b, c, etc. Once we get the exponents, whatever the common exponents are there, when they equal exponents, they can be grouped into one particular dimensionless parameter. In a Rayleigh theorem, if the x is a dependent variable, these are independent variables, we can write the exponents like this, and we can write the mass, because what are the fundamental dimensions we have? Mass, length, time, and in heat transfer you will get one more, that is temperature. But in fluid mechanics we get only 3. So by equating the dimensional formula, by equating the dimensions for the mass, length and time on both sides, we can calculate those exponents. Okay. And Buckingham pi theorem is more prominent. It should be written like this. If there are total n number of variables in a functional relationship, if there are total n number of variables in a functional relationship, I hope we understood the Rayleigh theorem. This has got a dimensional formula, this has got a dimensional formula, this has got, so we have to write the dimensional formula for all the things, and by equating the powers of the mass, length and time, we can calculate these exponents. Once we get the exponents, the functional relationship can be comfortably expressed. But this is of limited usage when the variables are lesser. But this is of more usage for a large number of variables involved in the function. If there are total m number of variables in a functional relationship, both dependent and independent, and if all the variables put together contain m number of fundamental dimensions, then the functional relationship among the variables can be expressed in terms of n minus m number of fundamental dimensions, n minus m number of dimensionless pi terms, n minus m number of dimensionless pi terms. If n is the total number of variables in the functional relationship, if n is the total number of variables in a functional relationship, and if all the variables put together contain m number of fundamental dimensions, then the functional relationship among the variables can be expressed in terms of n minus m number of dimensionless pi terms. For example, I'll just give the example here for this. Example for the Buckingham pi theorem. In any hydro turbo machine, like a hydraulic turbine, in any hydro turbo machine, like a hydraulic turbine, example hydraulic turbine, the power output of the turbine is dependent upon the head, diameter of the runner, speed, discharge, okay, and acceleration due to gravity. Okay, so total number of variables will be here 6. H is the head, D is the diameter of runner dia, or the turbine runner diameter, N is the RPM, Q is the discharge, G is the acceleration due to gravity. Total number of variables are 6. The number of fundamental dimensions will be containing in all put together is 3. What are the 3? Mass, length, time. Mass, length and time. Okay. I don't say that this all the parameters must have the mass, length and time. So total number of fundamental dimensions you see in all the variables is mass, length and time. Then number of dimensionless pi terms, dimensionless pi groups, pi terms will be n minus m, that is 6 minus 3, it is 3. So the functional relationship can be expressed in terms of pi 1, pi 2 and pi 3. The functional relationship just simply can be expressed in terms of these 3 pi terms, pi 1, pi 2 and pi 3. Discharge, RPM, speed, diameter of the runner, head, power, P is the power output. P is the power output of the runner. So this is an example to understand the dimensionless Buckingham pi theorem. Generally, after this, what is the use of getting these pi terms will be is, these dimensionless pi terms we are getting can be directly equated between model and the prototype. These dimensionless pi terms can be directly equated between the model and the prototype if there is a complete similarities existing. In the dimensional analysis, we talk about 3 kinds of similarities: kinematic similarity, before that we have the one more, geometric similarity, kinematic similarity and dynamic similarity. Okay, geometric similarity means similarity of sizes, angles, etc. Supposing one shaft is there, this is similar means this corresponding ratio of the sides will be, that means this diameter by this diameter is this length by this length, like that. So the corresponding sides, the ratios of the corresponding sides must be equal between the prototype and the model. Then they are said to be geometrical similarity. Kinematic similarity means similarity of velocities, of corresponding points, on model and the prototype. This is the prototype originally put in the application. This is the model that is made in the laboratory. Prototype is made in the put in the application, actual application. Model is manufactured in the laboratory. They maintain a similarity. Geometric similarity means similarity of the corresponding sizes. This diameter by this diameter is this length by this length. And the kinematic similarity means the corresponding velocities. Velocity of the prototype, here the velocity of this ratio should be equal to at some other corresponding points of the ratios of the corresponding points. Dynamic similarity means similarity of forces. of forces acting at corresponding points. Acting at corresponding points. Corresponding points between the model and the prototype. That is called as the dynamic similarity. Only when all three similarities are satisfied, there is a complete similarity. There is a complete similarity existing. That is called as homologous in series. They are said to be homologous in series. When the model and the prototype are homologous in series, those dimensionless pi terms that are obtained can be directly equated between the model and prototype. The main advantage of getting those dimensionless pi terms is, if there is a between the prototype and the model, if there is a complete similarity is existing, if they are homologous in series, then whatever the dimensionless pi terms we have got by applying the Buckingham pi theorem can be directly equated between prototype and model, provided conditions apply. They must satisfy all the three similarities: geometric similarity, kinematic similarity, and dynamic similarity. So that is the main essence of the then only that there will be a complete similarity or homologous in series. They are said to be homologous in series. Based on that only we define the specific speed of the turbine, etc. Okay. In the dimensional analysis, we come across 5 different dimensionless numbers. One is called as the Reynolds number, which I already defined. Inertia force by viscous force. Second thing will be the Froude number. Froude. Froude model law they also call. Square root of inertia force by gravity force. When the gravity forces are significant, then the Froude number will come into picture. Third thing is the Euler number. Euler number. You have to remember the definitions. Square root of inertia force by pressure force. We have to please remember these definitions in the dimensional analysis. Fourth number will be the Mach number. This definition is very important for the mechanical engineers also, because there is a compressible fluid flow. We always talk in terms of the Mach number. Inertia force by compressibility force, or sometimes they call elastic force. Compressibility force, or some books will also give it as the elastic force or elastic force. It is something talks about the compressibility effects of the fluid flow. And finally, we have the Weber number. Weber number, it is the square root of inertia force divided by surface tension force. These 5 definitions we have to remember, particularly in the dimensional analysis. Generally, in the Froude model law, this is called as the, in the Reynolds model law, it is for the incompressible viscous fluid flow. When the viscous forces are predominant, viscous fluid flow. But that means, for example, a high velocity viscous fluid flowing over the bodies, like a submarine. A submarine is flowing under the water with good velocity. Water has got a good viscosity, then definitely viscous forces will play a significant role there. That is called as the Reynolds model law. This is a Froude model law. It is the free surface flows. Free surface flows. With a ship is moving. Actually, a ship is moving. A free surface flows with waves. This then comes the Froude model law. Euler's model law, when it is when fluids are flowing under with the pipe flows with great turbulence. Pipe flows with great turbulence. Closed pipe flows with great turbulence. Then we may talk about the Euler's number. Mach number will be the high velocity gas flows. High velocity gas flows, and also water hammer, where the water hammer effects are important. Water hammer is connected to the water hammer effects. In all those cases, this Mach number will be, compressibility effects are taken into effect. In the Euler number, pressure force is the predominant. A closed pipe flows with great turbulence, that is the Euler number. Froude number will be the gravity, where the supposing free surface flows with waves, or flow from nozzle or orifices, nozzle and orifice. Then they are the examples for the Froude number, where the Reynolds number is the incompressible viscous fluid flow. Supposing a submarine is flowing under the water, where the viscosity plays a significant role, then the Reynolds model law, Froude model law, Euler's model law, Mach model law, Weber number. Weber number will be the, where the capillary effects, capillary waves, and low depth of flow flows, low depth of flow. Free surface flow with low depth of flows, very low depth, because surface tension forces are significant when the depth of flow is very, very small. Low depth of flows, there the Weber number will be taken into effect. So, in the dimensional analysis, what we have to understand is, we have to learn about all the dimensionless numbers, 5 numbers, and where each model law is applicable. Thoroughly we have to write them, each model law where it is applicable. So, in the Euler number, pressure forces are significant. That means closed conduit flow with a high degree of turbulence of the liquid, Euler model law. Like that, we have to remember where the particular model law is applicable. Okay. Now, last but not least, the very important topic will be hydraulic turbines. This is the turbo machines or turbo machinery. Generally, hydraulic turbine is a device which produces mechanical power at the cost of the hydraulic energy supplied to the machine. It is a prime mover. It is a prime mover which converts the hydraulic energy of water into mechanical shaft power. It produces mechanical shaft power, which in turn gets converted into the electric power, which in turn generates current electricity. Hydraulic energy available in the dam gets converted into the mechanical power by using that hydraulic turbine, which is a prime mover, a turbo machine, hydro turbo machine. Okay. And the main things what we have to understand here is the head of the water available. No? So the water will be, this is a dam. It is a dam. Dam is a masonry structure, right? It is a dam, a reservoir. This is a reservoir, water reservoir. Water is taken from the base of the dam through penstocks into the powerhouse, where a turbine is installed. This is our hydraulic turbine. When the water coming from through the penstocks, penstocks are the very big, large masonry concrete pipes, huge diameter concrete pipes there, which will be carrying the water under pressure from the base of the dam. So into the turbine, and here the water strikes the runner of the turbine and produces the mechanical power which gets converted into the electric power. So this is the final output. And after doing work in the runner, finally the water will be discharged. Water will be finally given onto the downstream side. This is called as the tail race level. This is the tail race. This is called as the head race. The difference between the height between the head race and tail race, this is called as the head of the water. The difference between the head race level and the tail race level is called as the head of the water available in the reservoir at the dam. So we are the hydraulic energy of the water, available in the dam, it is made once the water strikes into the runner there. This is called as the runner which is rotating, not rotor, use the word runner. So when the water is made to strike onto the runner blades, and there will be an exchange of energy. Torque is exerted, the same principle, the torque exerted is equal to rate of change of angular momentum, Newton's second law of motion only, but for a rotating body. When the water strikes the runner of the turbine, there is an exchange of angular momentum because of the torque exerted by the water on the runner, thereby producing mechanical power. Runner is made to rotate because of the exchange of angular momentum between the water and the runner, and that mechanical power gets converted into the electric power. So this is a basic principle how electric power is generated in a hydroelectric power station. Just wait a minute. Now, welcome back to the class. Now, based on the head available, based on the type of action, based on the specific speed values, we can classify the hydraulic turbines into so many varieties. See, we can classify the hydraulic turbines into based on 4 categories. One is based on the head available, number 2 based on the type of flow, number 3 based on the type of action, whether it is an impulse or reaction, and number 4 based upon the specific speed values there. Okay. Classification. Classification is very important. Based on head available. High head, medium head, low head. High head, when head available is greater than 300 meters, like that, 300 to 350 meters Above that, it will be, this is the Pelton wheel. Best example is, we have basically only 3 turbines in our GATE syllabus. Pelton wheel, Francis turbine, Kaplan turbine. Of course, there is one more turbine called propeller turbine, which is similar in action to the Kaplan turbine. We have only 3 turbines, very importantly, Pelton wheel, Francis turbine and Kaplan turbine. Medium head. Medium head means what? The difference between head race level and the tail race level. Medium head will be somewhere between 60 meters to 150 meters or 200 meters. This is the modern Francis turbine. And finally, we have the low head turbine. Low head turbine, if H is equal to 10 to 30 meters. Example is Kaplan, and we can also make use of propeller. The difference between these two is, in the Kaplan turbine, we have the adjustable moving blades. In the propeller turbine, you don't have the adjustable. The main important criteria of the Kaplan turbine is, main important constructional feature of the Kaplan turbine is, it has the adjustable moving blades. No turbine has that facility. As the turbine is runner is rotating, the moving blades of the turbine runner can be adjusted, can be tilted slightly. So that makes the Kaplan turbine very special in action, special feature. Therefore, its part load efficiency, because of that special feature, constructional feature available in the Kaplan turbine, it has the highest part load efficiency. The part load efficiency, the part load efficiency of the Kaplan turbine is the highest among all the 3 turbines because of that extra constructional feature. What is that? The adjustable moving blades. While that Kaplan turbine is very big because it handles the high discharge. Low head means very high discharge. Low head means very high discharge. High head means low discharge. This is the low discharge. It requires little water. Pelton turbine, which is there in the Paikara powerhouse near Ooty, it requires very little water because it is where the water is available at great heights. Whereas just 20 meters it is operating, 20 meters height of the water there in the reservoir, and the quantity of water required is very high. Yes. This is one important classification. Pelton wheel, Francis and Kaplan. Second thing is the type of action. This is very important. Type of action. Impulse turbine and reaction turbine. Impulse turbine. In the impulse, all the head of water available in the reservoir gets completely converted. Gets completely converted into kinetic energy. Gets completely converted into kinetic energy. Converted into Ke of water, kinetic energy of water, before it strikes the runner. Before it strikes the runner. By the time the water strikes the runner of Pelton wheel, it has only one form of energy, that is the half mv square, that is the kinetic energy. Because whatever the head available in the reservoir, that has been totally transformed into the kinetic energy of water before the water strikes the runner buckets in Pelton wheel. Okay. In the reaction turbine, the best example is only one impulse turbine we have, that is Pelton turbine or Pelton wheel. It has a buckets number of, so about 20 to 25 buckets will be there mounted on the periphery of the wheel. In the reaction turbine, only a part of head available in the reservoir only a part of the head available in the reservoir gets converted into gets converted into Ke of water before it strikes the runner. By the time water strikes just before striking the runner, only a part of the head available. Head means energy, right? No? Head means energy of the flowing fluid per unit weight. Only a part of the head available in the reservoir gets converted into the kinetic energy of water before it strikes the runner, before it hits the runner. But the remaining conversion of pressure energy into kinetic energy, occurs within the runner. That means only a part of the head available gets converted into the kinetic energy before it strikes the runner, and the remaining conversion of the remaining head gets converted into the kinetic energy as the water is passing through the runner, as you know, within the runner, that is, as water passes through the runner. That is why here the relative velocity of the water is greater than at exit. Water enters with low relative velocity into the runner. The main thing what you have to understand is the water enters with low relative velocity and leaves with high relative velocity. Why? The relative velocity of the water is increasing from inlet to the exit of the runner in case of the reaction turbine. Two examples I can give. Francis is reaction, Kaplan is also reaction, propeller is also reaction. All three turbines are reaction. Only one is impulse, that is Pelton wheel. Okay, why this relative velocity is increasing? Because the pressure of the water decreasing from inlet to the exit of the runner. Because the pressure of water is decreasing, the entire runner of the reaction turbine is completely submerged in a pool of water. Nothing is open. No part of the reaction turbine runner is visible outside, because the runner is rotating in the completely sealed water casing. Because water pressure keeps on decreasing from inlet to the exit, from a value which is more than atmosphere to a value lesser than atmosphere. I can say the pressure of the water leaving the runner of a Francis turbine is lesser than the atmosphere. Of course, there may be chances of cavitation because the pressure is falling less than atmosphere. I repeat once again, the pressure of the water, by the time the water enters the runner of the Francis turbine, when it just enters the runner of the Francis turbine, runner means rotating element, it is more than atmosphere at inlet. But as it passes through the runner, its pressure keeps on decreasing from a value of higher than atmosphere. By the time it leaves the runner, its pressure is less than atmosphere. You will see the vacuum pressures. You may see the cavitation. You may see the cavitation at the exit of the runner of the reaction turbine. There is a possibility of cavitation occurring at the runner exit only in the reaction turbine. No chance of cavitation here in the Pelton wheel. Why? Because it is an open jet, free jet. Free jet means open to the atmosphere. A free jet open to the atmosphere at atmospheric pressure strikes the bucket in the Pelton wheel. I hope you are understanding the difference between, it's a very important difference, that is pure impulse and reaction. Pelton wheel, here in this side Francis, Kaplan and propeller. Okay, this is a very important. Other things are very simple things. They are based on type of flow, direction. Based on type of flow. Tangential flow is Pelton wheel. Tangential flow. See, if this is the Pelton wheel bucket, there are so many buckets are there on the Pelton wheel, around 20 to 25 buckets. Water jet coming from the nozzle directly strikes and wheel will be rotating. No? Water enters, water strikes tangentially, after that it will return tangentially. This is a nozzle. Nozzle or the spearhead will be there. This is a simple Pelton wheel. Second thing will be mixed flow turbine. Mixed flow turbine, that is water enters radially and leaves axially. Water enters radially like this through the wicket gates and leaves axially into the draft tube. We have one extra important component in the reaction turbine, which is called as a draft tube. Draft tube will not be there in the reaction turbine. See, water enters radially, this is the runner, and leaves axially. This is the tail race level. The draft tube is completely submerged in the tail race level. So look at this, these are the runner vanes of the Francis turbine. Water enters radially and leaves axially. This is a mixed flow turbine. Here it is entering tangentially and leaving tangentially because it is a tangent to the runner. This is the runner axis, you know. Okay. Here this is the runner shaft. Shaft is rotating, you know. This is a radial. Water enters radially and leaves axially into the draft tube. There is no draft tube there. In the Empress turbine, no draft tube. Draft tube is there only in the reaction turbines. In the third one will be axial flow turbine, which is an example of Kaplan. This is Francis. This classification is Francis. That is Pelton wheel, this is Francis. In the Kaplan turbine, only 4 vanes will be there, only just 4 vanes. Water enters axially and leaves axially. In the Kaplan turbine, water enters axially and leaves axially. Only 4 blades. This is one blade, this is another blade, this is another runner vanes, backside one. Only 4 vanes. Water enters axially and leaves axially. This is the axis. This is the draft tube. Draft tube is there only in the Kaplan and in the Francis. Draft tube is there only in the Kaplan turbine and in the Francis. No draft tube in the Pelton wheel because it is a pure impulse. Those two are reaction. Those two are reactions. This one Francis and Kaplan are here. But Francis, it is a mixed flow turbine because water is entering radially, leaving axially, leaves axially into the draft tube. Here water enters axially in the Kaplan turbine runner and leaves axially into the draft tube. Kaplan turbine is the biggest among all the turbines. I already said it has got one special feature. The moving blades are adjustable. The moving blades are adjustable. While rotating, the moving blades can be tilted. Because of that facility, part load efficiency highest. Part load efficiency is one of the gate question asked. Part load efficiency highest for the Kaplan because of that adjustable moving blades feature prevailing only in the Kaplan turbine. Okay. Then fourth classification is the specific speed based on specific speed. Specific speed is very important term in hydraulic turbines. Specific speed formula will be n root p. You have to remember h to the power of 5 by 4. This ns is low specific speed for the Pelton wheel. Low specific speed for the Pelton wheel around 8 to 20. For single jet 8 to 9, or for multiple jet maybe up to 15 to 20. Medium specific speed for the Pelton wheel, Francis turbine, it will be around 150 to the 300. High specific speed is for the Kaplan turbine. Kaplan above 600. NS is greater than 600 to, it may touch up to 1000. Kaplan is highest. Medium specific speed is Pelton wheel, Francis, and low specific speed is Pelton wheel, 8 to 15 or 20. So this is the formula for the specific speed, n root p by h to the power of 5 by 4. H is the head, p is the power. So this is based on broad classification, and the generalized formula, generalized Euler turbine equation, generalized turbo machine formula, generalized turbine equation is for all the which is can be obtained, the power output, hydraulic power output of hydraulic turbine, that is work done per second by water on runner of the turbine will be mass flow rate of the water into VW1 U1 plus or minus VW2 U2. This is a generalized turbo machine equation, or which is also called as the Euler's turbine equation. Very famously it is known as Euler's turbine equation. A generalized turbo machine equation. So many watt. How much work is done by the water on the runner of the turbine? This is given by this, where VW1, and actually we have to make out the velocity triangles. VW1 and VW2 are virile components. Velocity triangles we should know. Virile components of absolute velocities. Absolute velocities of water at inlet and exit. One means inlet, two is exit. That is parallel to U, parallel to blade speed U, or runner vane speed, parallel to the runner vane speed U. So the component of the absolute velocity parallel to the U, that is called as a virile component. M dot is the mass flow rate. And in many turbines, one virile component may become 0. Particularly in the Francis turbine, VW2 is 0. Kaplan turbine is also VW2 will be 0. Only VW1 will be there. If you just look at the Pelton wheel velocity triangles, Pelton wheel bucket, semi-ellipsoidal bucket will be there. The jet strikes at the center of the bucket and it breaks it into two halves. In the Pelton wheel velocity triangles, if you see, it breaks it into two halves. It strikes here, this absolute velocity, and if this is the bucket speed, it is the relative velocity at inlet will be V1 minus U. this is the absolute velocity of the water coming from the nozzle, because in the Pelton wheel, from the penstocks water enters the nozzle, a converging nozzle, converging passage, where the head of the water gets completely converted into the kinetic energy. I already said, in Pelton wheel, the only form of the energy the water has while striking the runner is kinetic energy, right? So, with that kinetic energy it strikes, after striking that, it flows, it breaks into two halves. One half will go like this, another half comes like this. This is the velocity triangle. This is VR2, relative velocity, this will be V1 minus U, this is VR2. This usually, this bucket angle will be around 15 to 20 degrees. This will be the absolute velocity. This is the blade speed. This is the exit velocity triangle. Inlet velocity triangle is obviously a straight line. This is the blade speed, bucket speed. U is the bucket speed, bucket tangential speed, given by pi d n by 60. Okay, V1 is the absolute velocity. We can always write Cv into root 2 gh, where h is the head available. See, because all the kinetic energy of the water, all the head of the water gets completely converted into the kinetic energy, V1 can be written as Cv into root 2 gh. Cv is the coefficient of velocity of the nozzle. The purpose of the nozzle there is to convert all the kinetic energy of the water into the, to convert all the potential head of water into the kinetic energy. The purpose of the nozzle is to convert all the head available in the reservoir completely into the kinetic energy. So, this is exit velocity triangle. Exit velocity, this inlet velocity triangle is, this is V1, this is U, this is VR1. VR1 will be V1 minus U, straight line. No? Exit velocity triangle will be like this for the Pelton wheel. This is VR2, this will be phi, this is U, this is V2, this is the VW2. What we require is the VW2, the component of the absolute velocity parallel to the U. This is U, no? This is our main important component, which is called Virl component. This is called Virl component. What is the Virl component here? V1 itself will become the Virl component, because its component in the blade direction will be whole of that, because V1 and U are collinear. V1 and U are collinear. This is the direction of the U, right? The direction of the jet of the water and the direction of the bucket at inlet, they are collinear. That is why V1 will become VW1. This is VW2. What is VW2 here? VR2 cos phi minus U. So, this is the Virl component. But VR2 is almost equal to the VR1. I already said, no change of relative velocity as the water is passing through the runner of the bucket, because the pressure is constant here. How much is that? Atmosphere is a free jet, already I said. Water is passing at atmospheric pressure in the bucket. Therefore, the relative velocity should not change. It should remain same, but slightly decrease due to the friction, maybe 5-10%. You can take it as equal. So, VW2 we can write it as the VR1 cos phi minus U, because VR1 is equal to, neglecting friction, VR1 is equal to the VR2. There will be some little bucket friction will be there. Neglecting that VR1 can be taken as the VR2. So, this is how we can construct the velocity triangles for the Pelton wheel. That phi will be around 15 degrees usually. U is the bucket speed, already given, pi d n by 60. Okay. And then you can substitute in that generalized turbomission equation, power is equal to m dot into, here interestingly interestingly, U1 is equal to U2. In Pelton wheel, U1 is equal to U2 is equal to U, which is given by pi dn by 60. In Pelton wheel, the tangential speeds at inlet and exit are equal because it is a tangential flow turbine from which you can calculate the power output. And the very important definitions we have to understand here. The hydraulic efficiency of any hydraulic turbine will be work done per second by water. This is where usually it is, these questions are asked in the examination, divided by energy supplied per second at inlet to by water at inlet to runner. How much energy the water is having at the inlet to runner, that is the input. Output will be the how much work it is doing. It is called as the hydraulic efficiency of the turbine. This is a general formula for all the turbines. Work done per second by water on the runner divided by how much energy is supplied per second by water at the inlet to the runner. In both Francis and Kaplan turbines, generally it is taken that generally VW2 will be taken as 0. Generally VW2 is taken as 0. Therefore, work done per second will be m dot into VW1 U1. So many watts. Therefore, the hydraulic efficiency of the Francis or Kaplan, anything we can take it as the VW1 U1 divided by GH. Don't write for this and Kaplan also you could write. And don't write it for the Pelton wheel. Pelton wheel, it will be hydraulic efficiency formula will be different. This is the formula for the work done hydraulic efficiency in work done per second by water on runner. Okay, m dot is mass flow rate. M dot is the mass flow rate of water, which is density into discharge. Density into discharge. In Pelton wheel, if you just look at this, in Pelton wheel, the work, in fact, you can write this power in, because in Pelton wheel it will become VW1 plus VW2 into U, you can take in Pelton wheel. And here, supposing if you just want to write the hydraulic efficiency in Pelton wheel, if you want to write m dot into VW1 plus VW2, which you can obtain here. VW1 is V1, VW2 is VR1 cos phi minus U. U can be taken common, divided by half m dot into V1 square, because in Pelton wheel there is only one form of the energy the water has. Before striking the bucket, this is a bucket, semi-ellipsoidal shaped bucket with a sharp edge here. By the time the water strikes the runner of the bucket, it has only one form of energy, that is the kinetic energy. You can see here, I have just written the kinetic energy here. But that is not so in case of the Pelton wheel, in case of the Francis and Kaplan, water is possessing not only kinetic energy, by the time the water strikes the runner of the Francis and Kaplan, apart from kinetic energy, there is some other form of energy is also there, pressure energy by the time. The remaining conversion of the pressure energy to the kinetic energy occurs as the water flows through the runner of the Francis turbine. That is why the pressure of the water at the exit of the Francis turbine runner is less than atmosphere. That is what the function of the draft tube is. Why it is a function of the draft tube? Draft tube function, main function in hydraulic turbine is it converts the kinetic energy of water leaving the runner into useful pressure energy. Supposing if it is a Francis turbine runner like this, it is a Francis turbine runner, the function of the draft tube will be, it is a diverging passage, right? So it converts the kinetic energy of the water leaving the runner into useful pressure energy because it is a diverging passage. So here the atmospheric pressure. So here the pressure will be less than atmosphere. Here at the exit of the runner. This is a Francis turbine runner, right? So water is entering radially and leaving axially. So leaving at a pressure less than atmosphere. There is every possibility that there may be a cavitation. Cavitation at exit of runner. Only in the Francis turbine and also in the Kaplan turbine. So this is the draft tube which is converting the kinetic energy of the water into useful pressure energy, thereby creating a vacuum. Thereby you are getting a vacuum here. You are getting the vacuum pressure at the exit of the runner. So that you may get the more work. You may get more work done by the water on the runner. By getting vacuum, what is the main advantage? The hydraulic efficiency of the turbine may be slightly increased. Because the pressure difference between the inlet and the exit it is increasing, right? As the pressure difference increases, there may be more chances of work done by the water on the runner. Okay, that is why there is a likelihood of the cavitation may happen at the exit of the runner. Only in Francis and Kaplan. No cavitation in case of the Pelton wheel because pressure is same throughout in the bucket as the water passes through the bucket of the Pelton wheel, atmospheric pressure. So with this I would like to conclude the Crux synopsis classes. In these 5 days, I hope I did it judiciously, covering all the topics of fluid mechanics and hydraulic machines also. And I've done most of the gate problems, all the relevant, but give more focus on some topics like the kinematics of fluid flow, dynamics of fluid flow, applications of the Bernoulli, and flow-through pipes. Flow-through pipes is a very important chapter. Don't neglect that. Incompressible flow-through pipes, internal flow-through pipes, all very important chapter. So questions may come very often. So there are certain areas on the FM where you may be most likely to be asked questions in the gate examination. So practice the more and more questions. All the previous years of gate and previous years of the prelims of the IES. As you practice more and more problems, this subject becomes very easy. Very important subject in GATE. And this is Sekhar from Msigma Gokulam. I am giving my WhatsApp number also, 98494-10269. This is my number, personal number actually. You may call me also whenever you find a doubt, you may call me. I feel very happy to clear your doubts. Welcome to, I'm putting some WhatsApp groups in our Msigma Gokulam. We have created some Msigma Gokulam mechanical engineering community WhatsApp groups where I'm posting some questions. I'm conducting some polls, some quizzes there regarding these subjects, FM, TD, HT, etc. And you may be able to answer those questions and interact there also. You can call me otherwise. Okay. Wish you all the best. Good luck. So I hope you enjoyed my lectures in the last 5 days. All the best, my dear students. Good night. This is Sekhar from Msigma Gokulam. Bye.